Eutrophication is characterized by excessive algal growth due to the increased availability of one or more limiting factors required for photosynthesis. The most important factors influencing the development of phytoplankton are excess nutrients, nitrogen and phosphorus, from fertilizers, wastewater, and stormwater runoff, sunlight, and temperature. The most noticeable effect of cultural eutrophication is the formation of dense blooms of noxious, foul-smelling phytoplankton. These blooms reduce water clarity and degrade water quality. Chlorophyll A, a measure of phytoplankton biomass, is commonly used as an indicator of eutrophication. When these dense algal blooms eventually die, microbial decomposition significantly depletes dissolved oxygen levels, leading to hypoxic or anoxic dead zones that lack sufficient oxygen to support most organisms. Almost every analysis of the eutrophication process includes the spatial and temporal study of data such as chlorophyll, nitrogen, and oxygen concentrations in the water. In the project, we utilized data from the Baltic Sea biochemistry reanalysis dataset. These are model-based data that have undergone a reanalysis process. Originally developed for the Baltic Sea, the model is particularly robust in representing processes related to hypoxia and anoxia. The reanalysis process involves data assimilation, integrating observational data to provide the most accurate representation of continuous spatial and temporal fields of variables. 3 variables were used in this study. 1. Mass concentration of chlorophyll A in seawater, KIL. 2. Mole concentration of nitrate in seawater, NO3. 3. Mole concentration of dissolved molecular oxygen in seawater, O2. The goal of the presentation is not to conduct a comprehensive analysis of eutrophication, but to demonstrate how Xraster can be effectively used for such studies. Presentation structure. The presentation will be divided into 2 parts. 1. Analysis of chlorophyll A and nitrogen compounds. This part focuses on the surface of the entire Baltic Sea, analyzing chlorophyll A and nitrogen compounds, CHL and NO3. 2. Monitoring oxygen concentration. This section examines a subregion in the southern Baltic Sea, monitoring oxygen concentration, O2, at different depths, including the water column and near the seabed. Data and tools. We will work with 2 datasets. 1. A dataset covering the entire Baltic Sea surface, containing 3 variables, chlorophyll Al, nitrate, NO3, dissolved oxygen, O2. 2. A regional dataset for the southern Baltic, focusing on oxygen with data from various depths. Additionally, we will use a zone mask designed to align with the datasets. This mask has also been provided as a vector layer in shapefile format for integration into QGIS. Integration with QGIS and Xraster. To maximize the efficiency of working with Xraster, interactive use in QGIS is crucial. As part of the presentation, 2 brief demonstrations have been prepared. 1. Creating a zone mask from vector polygons in QGIS. This demonstration explains how to generate a spatial mask layer from vector polygons for use in QGIS and Xraster. 2. Processing text files created by Xraster's zonal statistics tool. This session focuses on handling and processing text outputs generated by the zonal statistics tool in Xraster, which are vital for spatial data analysis. We will begin the analysis by creating an average chlorophyll map for the entire Baltic Sea. We open the Xraster tool and input the data and mask. The mask contains a series of subareas of the Baltic Sea. Each subarea is assigned an identifier. Our dataset has 4 dimensions with a single depth defined as a range of the same values. We have 3 variables corresponding to chlorophyll, nitrate, and oxygen concentration. We proceed to subset to create a subset of the data for chlorophyll. By clicking OK, we will obtain an empty dataset. To resolve this issue, we need to specify the depth not as a range of values, but as a single value, such as 0. This will allow us to obtain a subset for a single depth. Now we proceed to the Statistics tab and create a map of the average chlorophyll concentration for the entire Baltic Sea. Since our data represent monthly averages from the years 1993 to 2023, Each pixel of the generated raster contains an average value calculated from 372 months. We will zoom in on the area of the southern Baltic Sea. Now we can check the chlorophyll concentration values. In open waters, the values are around 1 to 2. In the region of a sheltered bay, the values are around 4 to 5. In the most isolated part of the Vistula Lagoon, the concentration exceeds 10. We will select a point in a partially sheltered area and save its coordinates. We will now analyze changes over time at the selected point. We proceed to the Subset tab and create a subset for this point. Now we go to the Figures tab and create a time series plot of the chlorophyll concentration changes at this point. There is no clear trend of changes from year to year, but there is noticeable variability over the course of the year, repeating each year. We will conduct a variability analysis for the entire Puck Lagoon area. To do this, we will limit our dataset to this specific area only. We can see that in the mask, this area has the identifier 32. We will restrict the data subset to this area only using the mask. Now we will group the data into annual groups and calculate the average value from each group. The results will be presented in a graph. To do this, we go to the Group by Time tab. We select an annual grouping period and the mean statistic. We click OK and create the time series. We can see that until the year 2012, there was a clear trend of decreasing average annual chlorophyll concentration. However, after that, distinct fluctuations from year to year become evident. We will check how the variability looks from month to month. To do this, we will perform grouping by months. We can see that there is a clear seasonality in plankton bloom, with peaks in March and August. We will examine the seasonality in nitrogen compound concentrations. We will modify the data subset. We will group the data by months once again. We can see that there is a clear single peak in May. We will create a plot showing the annual variability of nitrate and compare it with the variability of chlorophyll. The relationship between the two variables is not obvious, but certain dependencies are visible. We will now analyze whether the concentration of nitrate on the surface of the Baltic Sea has changed over the last 30 years. To do this, we will divide the study period into two subsets. The first will cover the years 1993 to 2008, and the second will cover 2009 to 2023. We will close the previously created plots. Of course, they could have been saved both in graphic form and as data. We will create a subset of the data for the first period. We will create a map of the average nitrate concentration for that period. And we will save it to QGIS as a raster layer with the .tiff extension. Additionally, we will calculate the statistics of nitrate concentration for each zone for every month using zonal statistics, entering the identifiers of all the zones. We will save the results in a text file. We have obtained a text file with statistics for each month and each zone. Further processing of this data is possible in QGIS and other software. What we can do with this data in QGIS will be presented in an additional presentation. We will now create a subset of the data for the second period. We will create a map of the average nitrate concentration for that period. And we will save it to QGIS as a raster layer with the .tif extension. Now we move to QGIS and open the two created raster layers. We will subtract the layers from each other in Raster Calculator, creating a layer showing the difference in nitrate concentration. We subtract the older layer from the newer one so that a positive difference value indicates an increase in concentration. We can see that the range of values is from plus 27 to minus 65. We will apply symbology to the layer. We can now analyze where on the surface of the Baltic Sea there was an increase in nitrate concentrations. These areas are marked with shades of red, while areas where a decrease occurred are shown in shades of gray. We can also check the value of change at any specific location. Xraster and QGIS provide great opportunities for analyzing processes related to eutrophication. We will now focus on the third variable, oxygen. When oxygen levels become very low, the condition is referred to as hypoxia. We will analyze the occurrence of this phenomenon in the southern Baltic Sea, focusing on the Gdańsk Deep region. The dataset we will work with contains a single variable, dissolved oxygen concentration, measured in millimoles per cubic meter, which is equivalent to micromoles per liter. Since hypoxia is defined using the unit milligrams per liter, we need to convert the original measurement by multiplying it by 32 and then dividing by 1,000. We will introduce a second dataset, this time containing oxygen concentration in water at various depths. The data includes 29 levels, ranging from the surface to a depth of 120 meters. The first step in creating a data subset will be converting the original unit by multiplying it by 32 and then dividing by 1,000. We click the OK button and create a data subset containing all data converted to the unit milligrams per liter. Now we will create a map of the minimum oxygen concentration values on the seabed for the entire analyzed period. We go to the Statistics tab, select Minimum as the statistic, and create the map by clicking the Plot at Bottom button. In our analysis, as in most studies, we will assume that the threshold for hypoxia is less than 2 milligrams of oxygen per liter of water. We can see from our map of minimum oxygen concentration values on the seabed that such low values occur. We can explore these areas using the cursor and select a point where the oxygen concentration at the seabed is below the threshold value of 2 milligrams per liter. We will save the coordinates of the selected point. We will check how the oxygen conditions in the water column at this point have changed over time. We create a new subset in the Subset tab. We go to Figures and use Plot to create a depth-time cross-section at this point. We can see that low oxygen concentrations in the bottom water layer occurred episodically. However, there is a clear increase in the frequency of this phenomenon in recent years. The noticeable annual variability in the upper water layer is a result of higher oxygen solubility at lower temperatures during colder periods. We can see that low oxygen values in the bottom layer occurred, for example, in the summer of 2022. We will examine the average vertical profile of oxygen concentration during this period. We will restrict the data subset to August 2022. We will plot the vertical profile of oxygen concentration during this period. We can see that the concentration increases and reaches a maximum at a depth of about 40 meters, and then it gradually decreases to values below the hypoxia threshold of 2 milligrams per liter. The initial increase is likely a result of the decreasing temperature with depth, while the water remains fully saturated with oxygen. Subsequently, the oxygen concentration declines despite the continued decrease in temperature. To remove seasonal variability over the course of the year, we will examine the variability of the minimum annual values. We will return to the full dataset. We will perform grouping for the annual period using the minimum statistic and create a depth cross-section plot. We now see a clearer picture of changes in oxygen concentration in the analyzed part of the Baltic Sea. After the year 2020, a distinct 3-year period of reduced oxygen values is evident in the water layer from 70 to 100 meters. Interestingly, in the deepest layers, the oxygen concentration was higher during that time. We can leave only the areas with hypoxia on the plot by applying a filter when creating the subset to retain only data with values less than 2. Now the areas with hypoxia are even more clearly highlighted. We can also show how the area of hypoxia has changed year by year at a selected depth level. We will define a new data subset. We will calculate our data so that we sum the hypoxia cells for each year at a depth level of 0.90 meter. Since the sides of the cell are 2 kilometers in size, the cell area will be 4 square kilometers. We start by assigning a value of 0 to the cell by multiplying it by 0. Next, we add 1 or 0, which is the numeric result of the condition whether the value is less than 2. Finally, we multiply the value by 4. Please note that in the computational expressions, we access the data using the expression ds2.variableName. Of course, the value in parentheses must also be converted into the new units. To avoid counting the same area multiple times within a year, we will calculate the total hypoxia area for a single month, August. Now we can sum the area for each individual year. To do this, we group the data by years using the sum statistic and create a time series plot. We can change the way the plot is displayed. We can see that in the year 2022, hypoxia occurred over a large area, covering more than 900 square kilometers. We will adjust the vertical scale. In the other 2 years, 2018 and 2020, the area of hypoxia was smaller, while in the remaining years, hypoxia did not occur. Finally, we will create a map showing the seabed areas where hypoxia occurred at least once. To do this, we will modify our expression and use the entire data set. We will go to Statistics and perform a time-based summarization using Statistics Maximum. The seabed areas will be assigned values of 0 or 1. Click the Plot at Bottom button. We have obtained a map of the seabed areas where anoxia occurred. This map can be exported to QGIS, where an equal area projection can be applied to calculate the seabed area affected by anoxia over any selected time period. We will conclude our analysis here. Xraster is available for download from the following websites: